I send out the next assignment. Okay, this is closely based on what we did in the workshop. So if you have some catching up to do, you weren't in the workshop, come and see me. Okay. It, however, does not require what we did in the workshop. Everything in there you have all the tools have already been presented in class. Cool. Okay. Let's remember where we are. So we're looking at non-equilibrium simulations. And we looked at LD and BD, and we looked at boundary conditions, how they can tell us different things. So let's start talking about Monte Carlo non-equilibrium simulations. Okay, and let's start with off-lattice Monte Carlo. And this is pretty straight ahead. Get rid of this for a minute. Okay, so off-lattice non-equilibrium Monte Carlo. And let's just do it in one dimension for simplicity. And let's go back to what we have in Brownian dynamics, which is that our delta x is our external force over the friction coefficient, zeta, delta t, plus square root of 2d delta t random number, where the random number there has a mean of 0 and a standard deviation. Cool? This looks familiar to everybody? We're all cool where we get this from. This is just the equation of motion when we drop the inertial term. That's it. All right? Okay. And then we discretize v as dx dt. Okay? That's all we've done. Okay, so now let's look at having a particle here, and we're not going to have a distribution of random numbers. Okay? What we want to do is Monte Carlo. So in one dimension, what does my Monte Carlo algorithm reduce to? I don't need a distribution here. What does it become? Yeah, point flip. We either go right or left. Okay? So let's keep that. Let's keep a P plus and a P minus. And in fact, let's keep both of those to have the same probability, 1/2. Because we're off lattice, what we can do is change our jump. So we can have different jump lengths forward and back. Anybody want to pose some? What they could be? No, we don't even need that here.
So before
are we still forceless?
No, we got force right there.
So before we just had an increment of like 1, where we 1 by 1, right? Now can we just make
Well, we went A, an increment of A.
sorry, can we do like a probability of some scaling factor 2a? Like we can do anything from like 0 to 2a with either like say like
We can do that, but then we need another random number and all that stuff, right?
Okay.
So we want the only random numbers in our simulation in the Monte Carlo to be whether we're jumping right or left. What jump length do you think will give us the right answer? Any guesses?
Hold on. So the top equation, that was time stepping for Brownian motion.
Yep.
And we want to have a delta x such that if we flip plus or minus and move by that delta x, it recovers the same.
That's right. So,
2d.
not Martin. Anybody else by Martin's eloquent phrasing of the problem? Have a suggestion. So remember, what we're doing is in BD, this is distribution, right?
Mm-hmm.
It goes from, it's some Gaussian centered on 0. Okay. We want to get rid of that. Basically, just have it going right or left. Yeah. do you think the jump length should be? If I go forward, I'm going to have this contribution, right? And I'm also going to have this guy, right? Yeah, from the external force. So my forward jumps give you that. I really screwed up my. And how about my negative jumps? Pardon me?
We could still do
Negative of this whole thing? Yeah. No, because I have drift in my system, right? So my particle must bounce back and forth, but it also must drift to the right. And if the system's perfectly symmetric like that, right, your net drift is going to be 0. What do we want the net drift to be?
Say, so it's just the minus.
Yeah, exactly. Cool. This all right with people?
Doesn't this still put us on a grid though? Like, isn't our jumps still kind of contained by these units of?
You have two sizes now, right? So if you're here and you jump forward, you have some A positive, right?
Yeah.
But then if you jump backwards, you jump to here.
Right, because you're considering the drift as well.
Yeah.
Okay. That's understood.
Okay. So no, we have two different jump sizes. We are not lattice. Cool. So let's actually prove that this works, okay? So that was a little bit of intuition argument there. And being physicists, we're pretty happy with that, but Dan's in the room, so let's actually do. Oh, and Martin.
Oh, and Martin
demonstrated. Well, half of Martin. All right. So what we'll do, let's name this. What did you say?
The other half's not in the room. He's like, is that a bad joke?
Oh, okay. Strike that from the record. Okay, so let's just name our delta x to the lowercase f plus or minus lowercase r, just to simplify. We don't have to write this every time. Okay? This is f. This is r. Cool? It's basically the delta x that comes from our f and the delta x that comes from our radius. Cool? Okay. So, what is my mean delta x? Well, that's going to be the probability of jumping forward multiplied by f plus r, plus the probability of jumping backwards multiplied by f minus r. Yeah? Is everybody okay with that? So we've seen this type of argument when we first looked at Monte Carlo. Yeah? Okay, well, what does it reduce to? Well, both of these probabilities are 1/2. Right? The r cancels out with the r then. And the two f terms add up. We get 2, 1/2. We get f. Cool. Which means that our average delta x, which means that our drift velocity, which is just we can bring the delta t to the other side, is just going to be that. Okay, as we know it. Cool. Yeah. Everybody okay with that? Okay, that's the easy one. How about x squared? How do I calculate this? The average delta x. Sorry, no. The average. I'm sorry. This should just be x. And this should just be average x squared. How do I calculate this guy?
Yep. The probability of f plus r squared.
Yep.
And probably backwards with f minus r squared.
Yep. so we can, of course, expand this out. Let's put the 0.5 out in front. The probability f squared plus 2fr plus r squared plus 0.5 f squared minus 2fr plus r squared. What does that equal to? F squared plus r squared. Okay, but have we made a mistake? But I thought this was just supposed to be equal to our diffusion part.
And even if we had zero diffusion, we'd still be drifting.
Yeah, but how do we actually get the diffusive part? It is not equal to mean x squared. What is it equal to? So if I have something that's drifting and diffusing, right? If I just calculate all these delta x's, square them, am I going to get this diffusion part? No. The diffusion part is just these kicks back and forth. So what do we have to do? We have to minus off the drift part. Cool, are people okay with that? And that's why what we're interested in is the delta x squared here. Okay, we got to minus off that part, right? Got to minus off this drift part, and what is this equal to? Well, it's just going to be equal to average x squared minus the average of x squared. Okay, so that means we have f squared plus r squared minus f squared. And so we recover r squared, which means we recover our 2d delta t. And that is our famous equation for diffusion. Cool? Yeah? Okay, so this is pretty straightforward for this case. And so if you were to do a simulation, code's pretty easy. Okay. We just we pick a random number. If it's less than 0.5, we do f over zeta plus square root of 2 times d. Okay. And here we do f over zeta minus square root of 2 times d. Cool. Okay with everybody?
So this is equivalent to grounding motion in first and second moments of x. Do they differ in higher moments?
That's a good question. Yes. All right. And so what do the results look like? Well, we can go through and do the simulation, and I'll just show you lattice. So I set up a drift of, what did I set up? I think everything is, f is 5 and kt is, or zeta is 1, so it should be a drift of 5. So if you look at this plot here, you know, when it reaches a time of 1,000. Oh, I'm taking delta t just to be equal. Then I hit 5,000. Cool. This is my drift. And if I look at my second moment, it's really blowing up because it also has a drift in there. But if I take the second moment minus the first moment squared, then this is a plot of what I get there. And so this then is the diffusion. This is the slope we expect. Right. Cool. Because this is 2 times. All right. Cool, people? Yeah, it's pretty straightforward. So all you do really going from DD to MC is you go from a distribution of random numbers to basically just only picking that. And so you go to just from distribution of jump sizes to just 2 jumps. Okay, but obviously, if you do this long enough, jump sizes are small in the scale of whichever you're interested in.
What's the benefit of that? You're still generating the right number.
It's faster. Yeah. So
Where do you get it?
So we'll see more of that as things become more complicated. So at this level, they're not that different. Okay. But if you can set up a Monte Carlo simulation of your system, it is generally faster than the others.
It's also definitely faster to write.
Cool. Okay. So now let's try. That was pretty easy, right? So let's try and extend that to the on-lattice case. And for on a lattice, we can't do this trick of just changing the jump size. Okay, so we got to try something else. And we're going to see that it's actually not so trivial to figure out what we should do. Okay. So lattice Monte Carlo. Okay, so we know that our drift velocity should just be f over zeta. Okay? We also know that our diffusion should be kt over zeta. Cool? So whatever algorithm we propose, it must adhere to at least these two conditions. Cool? Maybe more subtleties in the higher moments, like Martin has mentioned. Okay? But if we can at least get these two right, and we make everything small enough, we'll probably have a pretty decent solution. Okay? So, let's also do something else at this point in time. Let's remember that the Einstein equation is this in 1D. Okay, and so let's use this to define a time scale, subscripted b for Brownian time scale. Okay, and we're going to consider that because we want to put things on a lattice now. We want particles sitting on a 1D lattice with a grid spacing of a. And so the time then is going to be a squared over 2 d naught. Cool?
What is that?
That's the time scale associated with one jump. Okay? Cool. It's just going to be a useful time scale to. Okay? But this is in the presence of 0 external force. The time scale for a jump in the presence of 0 external force. Yeah.
So I have a bad question. But we're dealing with my
No questions are bad.
and also you brought in a time scale for
I feel obliged to say that.
that. Okay, so we're dealing with Monte Carlo and randomly brought in a time scale for the ground. Is that because there's no inertial term for the first one?
Yeah, no, definitely. So Monte Carlo certainly is no inertial. Okay, so we started here at MD, we went to LD, and then to BD we drop inertia, and then to MC. Oh, so we're slowly zooming out. Okay, coarse grain. Cool.
Question, our a is squared because when we take the root of that, it's going to come back to just regular.
No, we're just solving for this delta t. Right? Okay. So when delta x is a, the delta t must correspond to the time of one jump. Right? So if this is a, then this is whatever time we're trying to define. Right? Cool. And then we just solve. Cool. Okay. that's all in the absence of a force. Now, let's apply a constant force to the system. Okay. And this means we can write a potential u of x be negative f naught times x. Okay. So I cannot change the jump size as we did in the off lattice method. What can I do in the on lattice method to try and incorporate wolf drifting? My jumps must always be A.
Can we just jump more with drift or against drift? Like kind of in the same way, like
What do you mean jump more?
so like
Like more often?
so like we
Or do you
have
mean further distance?
like a further distance because
No,
we're still
because we're
doing
stuck
this.
at A.
Oh, right.
So we could do that for some magic force that would yield 2A over here.
Right. Like, I
But
think
obviously,
like,
we're
I
very
could-
limited.
I could jump once because
We
of
have to
force.
quantize our force. So it's pretty
Fair enough. Yeah, I could say we jump once because of the force once.
Do you define the jump size to drift larger than the jump size?
Can't change your jump size, guys. We're on a less.
Okay.
But you can't change your time,
Change your time step.
your probability of jumping.
So does anyone want to suggest something else we can do besides Martin? You can change the time step. There's something even more intuitive.
Maybe need some threshold energy.
Yeah. Okay, so right now we want to stay with a method in which we always jump either right or left. Okay. We've been using the probability of jumping to the right and the probability of jumping to the left equal to each other. But if we have a drift, maybe we can just bias the jumps. Particles jump in the direction of the drift. Seems like a pretty reasonable way to go about things. Yeah?
Yeah.
Y'all agree with me? Yeah? So we want to play with the probabilities. Okay? We want to play with P positive and P minus. Cool? How the heck are we going to choose what our new probabilities are? Oh, we're so confused. Does anyone have an idea of what we could maybe use to help us make this terrible decision? Well, we know the potential energy at any of the sites. Is there any way we could use that to inform our decision? Yeah. Okay. So what we're going to do, remember the Boltzmann distribution, okay? It says rho of x is proportional to negative u of x over kt. Okay? So if we consider, the long time equilibrium solution, if we had a reflecting wall here, what the density of particles at this site as opposed to that site would be, let's just call that rho plus over rho minus, that would be equal to negative u plus minus u naught over kt. Cool. What is that equal to?
Dealing with rows or P?
Those are rows, okay? Because I'm trying to do it directly from Boltzmann. Okay?
And row naught is at the current location.
Yes. What does this reduce to? Any position. If you look at the potential energy here, minus the potential energy here, what do you get?
Our f naught minus or f naught x minus or f naught f positive at x. Like should just be the difference in our potential energies.
So this, let's say our origin is over somewhere here, right? So this is 1, so this is 2A. This is 3A. Okay? What is this energy difference? What's the energy here? Yeah, it's negative 3A epsilon. Right? What's the energy here?
Negative 2.
Negative 2A epsilon. Cool? Are people okay with that? We're starting at, in this formulation, we've taken our zero potential energy to be where we start.
Okay.
Right? And since the force is in this direction, your energy is going down. Right? Cool? Okay? So, what can I write up here? The numerator of this argument. A of 1. Okay? Cool. Okay. So what I actually want to do, and we'll see why this is handy in a moment, let's define a dimensionless force to be F naught over 2. Okay. Including that 2 in there is going to be in later. It doesn't really matter if we include a 2 in there or not. Okay. What it will do is eventually it will change your time step. Okay, it'll change your probabilities a little bit, but everything will work out. Okay, so what I want. Pardon me?
Is that still F naught?
Yes, it should be F naught. Okay, so what I really want to get to is my probabilities. And so my positive jump is going to be proportional to E to the epsilon. And my negative jump is going to be proportional to E to the negative epsilon, because I'm just going in the other direction. It's all the math still. Cool? Yeah. But what's another condition that we have on these probabilities? Sorry. They're 50-50. No, it can't be. The whole point is that we can move away from that because we have fixed jumps. Is there another constraint on these probabilities?
Obviously, these probabilities still matter.
Yes.
So there's no chance of staying in the correct bit.
No, there is not. Not for now. Okay. That will be version 2 of our algorithm. Okay, so what does that result imply for us? Well, it tells us then that P positive at epsilon is going to be equal to E to the epsilon over E to the epsilon plus E to the minus epsilon. And if we divide everything by E to the epsilon, we get 1 over 1 plus E to the negative 2 epsilon. Cool? Yeah? Why did I write it this way? Well, because if I take P to the minus epsilon, that's going to be E to the negative epsilon over E to the epsilon plus E to the negative epsilon. And so if I add this plus this, what do I get? Not a trick question. 1. Cool? So our net probability is conserved. Which is good. And again, we can write this 1 over 1 plus E to the 2 epsilon. Okay, so with these probabilities, let's calculate what our delta x equals. Okay, our average position. Sorry, not our delta x. Our mean first moment, so our average position. Cool. So what's that going to be equal to? It's going to be equal to P plus times A plus P minus times negative A. And so if you take these definitions, what you're going to get is an A out front, e to the epsilon, over e epsilon plus e to the negative epsilon, minus e to the negative epsilon over e epsilon plus e to the negative epsilon. Cool. Anybody know what this thing is? Shorthand for that guy is? Oh, this is a thing. It is a thing.
Tangent for hyperbolic tangent.
It's a hyperbolic tangent. Okay? Remember your hyperbolic sine is basically e to the x minus e to the x over 2. Your hyperbolic cos is e to the x plus e to the negative x over 2. So if you take that sine of x over cos of x, you get this. Cool? Okay, no problem. So in order to, what we can get from this is that in order to obtain the result that we need here, okay, so yeah, so this is over just one jump size, okay? I'm doing this for just one jump, okay? So in order to get the correct result here, my average x for one jump, I said, is a tan hyperbolic epsilon. Yeah? But we know that v is equal to, this should also be in f naught, f naught over zeta. Right? And we know that v, our drift velocity, is going to be our average x over our average time, where each of these are just one step. Cool? Yeah? So we know this is equal to f naught over zeta. And so we can define this time to be a squared zeta, using that result in here. Hyperbolic tan of epsilon over 2 kt epsilon. Okay, where we have used that our f naught is equal to 2 kt epsilon over a. So I'm just plopping in what epsilon, what my f naught is here in terms of epsilon.
Is that the average time?
This is defined to be the average time. So the average is really implicit in our definition of time. Yeah. So these are redundant here. Okay. So really, tau is average time for one jump. Cool. All right. Is this cool with people? Yes, no, maybe? Okay, so what I'm doing is I'm taking my delta x result and popping it into here. And remember how I defined epsilon to be whatever we defined? Okay, I can write f naught in terms of epsilon to get rid of f naught, and I get this expression here. Cool. Well, if we compare that to here, then look, kt over zeta is our d. Okay, and so we have a d in here, and so we have, this becomes d, and we have a squared over 2d naught is our tau b. Okay, so in order for our algorithm to be correct, we must redefine our tau to be hyperbolic tan of epsilon over epsilon times what we would get in free space. Cool. Yes, no, maybe?
And so we need to use that as our time step.
Exactly. Okay. So we can go ahead and do this algorithm on a lattice. We will get the correct drift velocity as long as we consider this to be our constant. Cool? Yeah, so we satisfy this condition, which we know we must. If we don't satisfy these two conditions, something's wrong with our algorithm. As long as we define our time step. Cool beans? Any issues with that? Everything's great so far, okay? But now, let's look at what happens with the second. So, as always, this is going to be p plus times a squared. Again, I'm doing it for one jump. Okay. My one time step minus p minus negative a squared. Yeah. And so we just have an a squared up front, and we get p plus. No, sorry, this is a plus b. The minus is a. All right. Yeah. And so we just get a squared times p plus p minus. What is p plus p minus equal to? 1. Okay. So this is just equal to a squared, which actually seems like an encouraging result, right? It's not too bad. It's pretty good. But remember, what we really need here is this guy. Because what this boils down to is a squared minus a squared tan h squared of epsilon. And then our d, the Einstein relation, is this delta x squared over 2 time step. And so this is a squared times 1 minus tan h squared epsilon over, and if we plug in what tau is equal to, we're going to get 2 tan h epsilon over epsilon, and then a TV out here. Cool. And then you can do some trig math and stuff, okay, that I'll leave as an exercise. And what you ended up reducing this to is a squared over 2 tau b epsilon over sinh epsilon and cosh epsilon. Okay. Does anyone see a problem with this? Or is this okie dokie?
The tau b, is it 2 tan ht divided by epsilon tau b? Is that like a multiplier or is that like a multiplier?
No, the epsilon on the denominator is underneath the denominator.
Yeah, this is under the tan.
Okay, and the tau b by
Yeah, yeah, because what I'm doing is I'm popping this in.
okay.
Cool. So is this a satisfying result? Are people okay with it? You just believe me at this point, or is there a fundamental issue?
But this forces to choose a specific A.
Which is no good. You can't have our algorithm dictate that, right?
Because that would define a lot as well.
Yeah.
So yeah,
The results must be lattice.
so if we fix K, P, A, and F, we're not guaranteed that it
No, because our diffusion coefficient depends on the external force. What do we do? What do we learn from our simulations where we have both drift and diffusion?
They're basically independent.
Yeah. So if we just look at a Gaussian going across, right? It's drifting this way and it's spreading. But the mean is just going at the drift velocity. And if you take away the drift velocity, this thing is just spreading in space according to D. Cool? So D cannot depend on us. Yeah?
What's tau b?
That's, just think of it as a number.
But it also
It's
depends on
8.
It depends on the knot, which is what it's supposed to. So the right hand side should reduce the knot, but it actually reduces the knot. That's not.
Yeah.
But no, it,
Well, left.
So, but the point is that we have a diffusion coefficient that's changing with epsilon.
Yeah.
Okay. And in fact, if you plot this out, the bigger the force, the smaller your diffusion coefficient. Cool.
So this is not easy to just quickly do.
No, this is no good. Okay. Well, I'm not going to say it's no good. So let's actually look at simulations. Pull it up here. So this is our off lattice one. So here's our naive lattice Monte Carlo. Okay. And so what I'm doing in here is I'm defining, based on my f, I define my epsilon, and then I can define my probability of jumping forward and backwards. Okay, just like we saw. And now when I do my algorithm, I say if the random number is less than the probability of jumping backwards, I'm going to go negative one site. Otherwise, I go forward. Cool. So if the probability of jumping backwards is 1/4, then only when this random number is less than 0.25 will I go negative. Otherwise, I go forwards, and otherwise, I go forwards 3/4. Cool. Yeah. Okay. So this is what it looks like, and if we do this for a low force, okay, force of 0.1, and I show you what the results look like. Okay, it's a force of 0.1, so if I just look at, first of all, my average position, then at a time of 500, again, my time step is going to be 1 here. I've only gone 50 because I drove velocity. Cool. And if I look at my P, which is my second moment minus my first moment squared, so it's proportional to this. Okay, this is 2 times T. Then I still get, I'm going to 1,000 and some 500. So actually, if my force is low enough, this. Okay. Well, let's see what happens when we push it higher. Let's do a force of 5, like we did in the other one. Okay, come here. Let it run very quick. Okay, and then I'm just going to pull the data back in. And now I have a force of 5. So when I've gone 200 time units, then I've got 1,000, because the drift velocity is 5. And if I come over here and look at what my mean squared displacement looks like, so I take the second squared.
That's no good at all.
No, it's not very good. Okay?
Practically.
And it's barely increasing here. Okay? So remember, it should be twice the time, right? And I've only got about 40 and 200. Cool? So this breaks down when you get to forces on the order of 1 or something.
I think it's because we're not accounting for the correlation and only go for the concept.
No. It's just a limitation of this. So how can we get around this? The ideas. We want to do a new and improved version. We can't play with the spacing A. We played with the probabilities. So we have another degree of freedom that we could tweak.
We can play around with our time step itself, is how often we're going to be calculating.
We can play with the time step. Okay, and so what we can do is we can take a distribution of time steps. If we map that appropriately, then we can recover both the correct B and the correct B. Okay? I don't want to do that. Okay? And why I don't want to do that is that it gets confusing for a simulation where you can have a particle here, two particles here, and they both jump in this direction, but then all of a sudden their clocks go off. Right? It would be nice if we can have basically a wall clock that the simulation progresses. This is a nice feature. If we can get it. Cool. So is there anything else we can do? I gave the answer away earlier in the lecture. What's a way of kind of effectively changing the time step without changing?
Oh, allow particles to stay off the correct spot.
Yeah, let's just introduce another probability. You can jump forward, you can jump backwards, or you can stay where you are. Cool. So this degree of freedom will then allow us to satisfy both of these. Cool. People on board with this? Yeah? This is just an exercise in how lattice simulations can be. Okay? Nice because you can use integer math, right? But you gotta be careful. Cool? Okay. So, what do I mean by that? Okay, and what I'm presenting is based off of work that was done in the former group I was in, and I end up using some of the results. And again, this is a good project. Okay. So, because I'm not going to go through all the details here, let's define a new set of probabilities, P plus and P minus, that are going to be 1 minus our probability of sitting still times our old probability. Cool. We're going to define a new time step, which also is going to be 1 minus PS multiplied by our old time step. Okay, this is not tau b, this is our old time step that we derived. Cool. And the probability of sitting still, this is something you can derive, and maybe someone will do it as a project and they can derive it for us. Okay, is equal to that.
The cosecant heck well? That's gross.
Oh, I'm missing a C here. Cosecant. You're one of the math guys. You're not allowed to say that. You're only allowed to say both. Cool. So I want to derive this, but instead, let's go through our exercise of calculating the moment to try and show that this existed. Okay, and so delta x is p plus and a plus a negative times negative a. And so this is going to be 1 minus s p plus minus p minus. Okay, and you can show that this is equal to 1 minus s hyperbolic tangent of epsilon. Sorry, this s is p sub s. Probability of sitting still. So this is really messy to do. And I did go through and do it, but you got to sub in what your PS is equal to. You got to sub in our old definition for P plus minus. Okay, but then indeed you get this result. Okay. Cool. Do you guys believe me? Okay. And from this, you can show that this is equal to V equals F naught over Z. okay, which is the condition that we need. And then you can do the same thing for delta x squared, and then you can calculate, oh, sorry, for x squared, then you can calculate delta x squared. From that, you do indeed derive that d is equal to, d naught is equal to a squared over 2 times tau, as required.
Hyperbolic cosecant is being defined as like that. That's all true.
Yep. No, yeah, I have to derive. I have to define it in functions when I program these.
What?
Yeah.
I don't know why it's complicated, but
Okay. So we might see that right here. Yeah. Okay. So here I'm going to set up a very similar simulation, but I'm going to define probability of sitting still to be equal to this. Cool.
are we supposed to see that?
Oh, yeah. Thanks.
Like, wow, it looks so
Yeah, cool.
Okay.
Cool. So we covered this up, but remember this is the cotangent here. Hyperbolic cotangent. Cool. And this is my cosecant here. So I'm not even defining it. That also is not a probability of jumping forward is going to be 1 minus PS times my old definition here. And same with the probability of jumping backwards. Cool. And this is my new tau, my new time step. Yeah. And other than that, all of this is the same, except now, remember we had 1 minus, sorry, if we had the random number was less than the probability of jumping back, and otherwise it must jump forward, right? But now we have the random number is less than p back, you jump backwards. Else, if it is less than p back plus p forward, you jump forward. Okay, and the else there is if it's not either of those, you sit still, you don't do anything, so just cool. Does this make sense to people? This little bit of code here.
Mm-hmm.
Yeah, because we have 3, it's very easy to see visually. We have 3 probabilities, okay? And they must go between 0 and 1. And so let's put our probability of going backwards here. Okay? And then our probability of going forwards is going to be in the direction of the drift, so it's going to be bigger. This is our probability of sitting still. Okay? So if my random number lies between here and here, go back. But if it lies between here and here, go forward. And if it's neither of those, you don't do anything. Cool? Okay, so that's it for the simulation. You can run the simulation. Does it work? So this is we incorporate probability of sitting still. And this is for a force of 5. So remember, this did not work in our naive method before. But now with a force of 5, we again 600 and 120 here. So our drift velocity is correct. And if we go back, if we go down to the diffusion coefficient, this is also correct. Okay, we're 200 and 100. Cool. So now with this extra degree of freedom, by just adding a probability of sitting still, we can satisfy both the correct drift and the correct. Okay. Again, there may be subtleties in higher moments and stuff like that, but we got the important stuff. This is probably going to work pretty good. Cool. It's all right with people? Okay. So lattice stuff you have to be careful with. Okay. But when you can get a lattice to work, it can be awfully fast. You don't have to calculate this distribution of jump sizes. You either go right or left. That's it. and they go the same distance. Okay, so you don't even need to keep track of your position of the float. It can just be integer, where your integer is just your locational velocity. Cool? But you must be careful when doing lattice simulations. Setting them up. Cool? And people do crazy stuff, okay? Because they even do polymer simulations on lattices.
Wait, what?
Yeah, okay? And so we have like a bond fluctuation model, where if you're here, you don't know, and your neighbor's right here, but if you're in 2D, well, then you can be here, or here, or here, or here, with probabilities, okay? And then in 3D, you can do the same thing, just do it this way, right? You can actually get pretty good results out of it. Yep, but again, you must be careful, because you're just using a lattice, you're imposing a huge constraint on your system. A constraint that can really speed things up for you, but if you're not careful how you implement it, it's pretty crazy.
So we here did all this for a potential that was for a constant force, right?
That's right.
So if we had a more complicated potential, we could do the same thing and go through.
Everything's the same. Yeah. This actually is agnostic to the how it looks, how the potential looks.
But epsilon is different.
Epsilon will now be a function of your lattice position, right? And so that can change your probabilities going forward and backwards, and it changes your time step.
Yeah. So what time step do you use?
You use whichever one for whatever jump you're looking at. So you have to keep track of different clocks.
So your particles desynchronous.
Exactly. Yeah. Which is not great, but manageable. Cool. Okay. So this leads nicely into the next topic. Because for the next little bit, what I want to talk about is just Monte Carlo simulations. Okay? So again, MD is just Newton. That's it. LD, we include solvent explicitly in the equation of motion. Okay? We're still Newton. ED, we get rid of inertia. So we assume overtakes. Okay? Now we went up to Monte Carlo. We don't have an equation of motion anymore. Things are just jumping around according to probabilities. Okay? And we built this out of our particle model so that I could show you guys, at least, this is one way of looking at them, so that you have a physical basis for what you consider a Monte Carlo simulation. Okay? But the idea of things jumping around according to some probability is obviously much more general than just looking at dust and water diffusing. Okay? In fact, we can use this to simulate a great many systems. Anybody have any ideas? Things moving around, probabilistically things are happening.
You should be able, well, I mean, we can immediately get back into gas law with that.
Yeah.
Right, for sure.
Yep, you have to bring in interactions if you want to look at like van der Waals and stuff like that. But sure. Sure. Diseases, that's a great one. Anything else?
Nuclear reactor.
Nuclear reactors. Nuclear reactors are an awesome one. And we'll talk about that. Anything else?
Optics.
Sure. So the question is actually more, what can't you model with this? Okay, if you can come up with a good model for what these probabilities are, right? If you can somehow get some information on that, you can model just about anything. Cool. You can model people in a mall. They diffuse around a little bit, and they also have a drift effect, right? So at each location and then a nice XY coordinate, we'll have some probabilities that you can calculate for this stuff.
Especially if you fly, but
Yeah, where the electric field is like, I don't know, like a Black Friday sale. That's a very strong one.
Yeah.
Cool.
Yeah. Just all the pieces around and goes through the net. Around,
So we can do lots of stuff. And some of the stuff we'll talk about, people are now using for, they're using stat-mech ideas, because remember a lot of this is founded in stat-mech, right? And they're using stat-mech ideas now to look at like, social dynamics, right? How will a group of people reach a consensus on an opinion, consensus opinion, if they do at all? Okay, and we'll talk about that. Cool? But this really is, we're now at the level, of course, playing so much out that the techniques we can use can be used to model so many different things. Okay? And again, it's all from a particle-based, agent-based perspective. Cool? So we're not writing down equations that govern the evolution of the system. We're breaking it into discrete little parts that are going to behave according to some rules, some probabilistic interactions. Cool? So what we're going to talk about now is going to touch a lot on what we're going to come back to in a couple lectures, which is just going to be just rule-based simulations. Okay? And so Monte Carlo is a part of the rule-based simulation, but I want to spend a bit of time just talking about different Monte Carlo approaches, just so that you have some exposure to it. Cool? Okay. So to do that, let's actually go way back to the beginning. Okay? And one of the first interesting things we talked about, and one of the first interesting discussions we had, courtesy of Matt, okay? Remember, when I started talking about Monte Carlo, so this is going to be a new topic, okay? Monte Carlo simulations at large, okay? Just in general. Where did you guys first see Monte Carlo in this class? Anybody remember? What did we do with Monte Carlo simulations? It's
Generated random numbers.
Wasn't the 1D back and forth probability?
no, before that we saw it. We're talking about games that you play in the bar where you're drinking.
Darts.
Yeah, and what did we do with our whole dart analogy?
Sampling distributions with random numbers.
Yeah, we calculated something, right? Yeah, we basically integrated the area of a circle by looking at projections, right? We said, well, we can do this for anything. So if we have any distribution, right? And we want a random number drawn from this distribution, okay? So it's something crazy, okay? We can't invert this, we can't use that method, okay? Certainly not a Gaussian, we're not going to use box ruler. What can we do? Well, we can draw random numbers, okay, over the domain of whatever function we're looking at, okay? So we can even say if it's finite, right? So it goes from 0 to L, okay? We can draw random numbers in this domain, and then we have an upper limit here, okay, that we can arbitrarily set to 1, and we can normalize our function so it never goes above 1. We can draw random numbers, and wherever they land, okay, we draw another random number to see where on the y-axis they land. And if they land outside, if they don't land underneath the curve, then it doesn't count towards the area underneath the curve, which is what the integral is. Cool? If they do land underneath the curve, then it does count. And so we can come up with, basically, this is a rejection method. So how many do we accept over the total? The total is going to be the area of this whole region, right? Because these are totally uniform numbers. And so the number we accept over the total that we drew is the area underneath this. Cool? Yeah? Ringing bells? We talked about this? It's all right? Okay. So as soon as I presented that the last time, there were some objections. Okay? And so let's take a function that it looks like this. Okay, so it could be like a Gaussian, let's say. And let's say we have it over a very large domain. Okay, so from negative L to L, where L is a big. Cool. What's going to happen by trying to do rejection sampling? Yes. Why?
The L's are large and you have a lot of random numbers generated.
Yeah, because most of them are going to be in blank space. Right? So is there anything we can do to increase the efficiency of this process?
Figure out some kind of envelope and renormalize.
Could. That sounds too complicated. Anything else? So that was Matt's idea.
Before we talk about defining the block size, instead of the block size.
Yeah, so that's what Martin's just saying.
Oh,
What if we found the distribution of 1 over x from this? No.
So let's abandon this idea of throwing our darts randomly. Okay? Let's try and use the information about our function to guide how we sample things. Cool? And so if I throw a dart here, okay, my next one I'm not just going to throw anywhere, but I'm going to throw it somewhere in the region. And I want to bias where I throw it, basically be where I have more probability of hitting. Cool? And so what I can do is say, okay, well, if I jump in this direction, and I look at the probability of being here versus being here, I have a higher probability of being here. So let's jump there. Cool? And if I look in this direction, I have a lower probability of being here than where I currently am. So let's jump there only if our random number passes a check. Cool? And if it doesn't pass a check, let's just stay where we are. We're probably better off.
what do you mean by passive check?
We're going to talk about that. Yeah. Cool? But we're always going to jump if we're more likely to be at that location. Cool?
So what happens when we have a very top level distribution?
Yeah, so we'll talk about that. First of all, let's answer this question, what's the check? Okay? So let's calculate the probability of going from x to, let's call it x test. Okay? This is where we propose that we jump. It can be right or it can be left. Okay? And this is just going to be the function at x test over the value of the function at x. Cool? Yeah? And so then let's draw a random number. And if the random number is less than this probability, jump. Cool? Yeah? So, if you're more likely to be at the position, this is greater than 1. And a random number will always be less than 1. Or equal to 1. Cool? So you're always going to jump. If you're more likely to be in that position, you jump. If you're less likely, you do so only with this probability. Cool? And so if you're much less likely to be to the left, then you'll rarely jump, and you'll stay to the left.
We have to renormalize?
No, because this.
But so we can't always jump to the right if we're something's going to jump to the left.
No, so you first pick a random number to decide, are you going to try and go right or left?
Yeah. And then if that says go right, I'm going, in this case, if it says try to go right, we all go right.
Yes, in this case.
And
Yeah,
if it says
but
try to
over
go
here,
left,
no, that's not true.
right.
Cool. Is this all right with people? So we first select a random number to decide if we're going to go right or left. So I asked if this was okay with people, and then when not, it was Austin who was out of the room. So it's not a good indication. So we first pick a random number to decide if we're going to try and go right or left. Okay? And then to decide if we actually execute the jump, we look at what our relative probability of being at these locations is. Okay? So if we're more likely to be there, which would be this case here, then we definitely jump.
Would you define this like jump size, I think, or just a random number?
Yeah, no, you can define the jump size. So, yeah, it'll be whatever.
So do you always start along the function? Like, with, like the
No, so this is, we're actually not we're actually not jumping like this. We're only jumping right in that.
So if your very first one was just off in the middle of nowhere, like the random number, then you're more likely to go towards where the function is.
Exactly.
And you'll just continue to jump until you hit it.
Exactly. So if, like, I mean, there's still tails here, right? If it's Gaussian, they decay quickly, right?
Yeah.
But there's still tails. And so even if we're somewhere out here, right, we're more likely to jump in this direction, right? And so if we're somewhere out here in the wilderness, where by our naive scheme, we would spend a lot of time drawing random numbers in blank space, we now start walking towards where things are actually happening. Okay? So this is called important sampling. This is what is important, and we want to get there, and we want to take most of our samples. Cool? But we can't make it a strict rule. Because if we make it a strict rule, then we'll never, if we start here, we would never see this part. Cool? So there still must be some probability that you go against the top. Yeah? Okay, so we bias, basically, instead of randomly drawing x positions down, we basically have, we're taking a walk through phase space that is guided by what we know about the function. Cool? Yeah? All right with people? Okay, so one thing I'd like to note, if f of x comes from u of x, then this probability is equal to negative u at x test minus u of x over k. Okay, I just want to make this connection. Cool, again by Boltzmann. Okay.
F. So F is the cumulative distribution? Or
No, it's just the function.
F is rho.
F is rho.
And
Yeah.
U is the
So if
integral.
yes.
So U is the cumulative.
Yes. Hey, does anyone know what this algorithm's called?
Did you just say it's important?
Yeah, but it's also called something else. A lot. A certain type of Monte Carlo. Metropolis Monte Carlo. You guys heard Metropolis Monte Carlo? Yeah, you must have, especially you surface materials people. Okay, Metropolis Monte Carlo. Okay, and so this is Metropolis Monte Carlo. You basically form your jumps according to a probability. Does it take you lower in energy? Then you definitely do it. Does it take you higher in energy? You do so only with some probability. And the higher it takes you in energy, the less likely you are to jump. And the weighting goes as the exponential of the weighting. That is Metropolis. Cool? Okay. And we'll see some more examples of that. What I'm doing right now is basically, we're still talking about drawing random numbers according to some distribution. And so this is what my code looks like. So I can start my x wherever I want. I started it at 0 here. And the function I'm going to use is going to be cos of x plus 1 over 25 times x squared. Why did I pick that? Picked it so that the distribution, the potential is shown in red here. And so you can get the distribution by taking e to the negative of that, right? And so the distribution is shown in. This is a distribution that I want to draw a random number. Cool. the blue. Okay. How do I do that? Well, this is my f of x here. And so I'm taking, which really should be my u of x. So my probability is just going to be the exponential between my test site and my current site. This will give me my probability. Cool? Yeah. And I take a random number, and if my random number is less than p, then I set my x to equal x test. And if it's not, then I stay where I am, so I do nothing. Cool?
So this is equivalent to having a particle moving in an energetic potential given by like the logarithm of the cumulative.
That's right. But we'll make that connection later. Now we're just drawing random numbers according to this. Cool. Everybody okay with this? So we're not selecting random numbers in X between on our domain here anymore. My X position, the next one I evaluate is going to be based on my previous position. But that's the only thing that is based on. Okay? Again, it's a Markov chain. Only connected to your previous. Cool. So this does actually work. Well, let me take my random numbers, so my x's. Okay, and notice I'm not throwing anything away here. No rejection. Okay. Sometimes I sit still, but that still gives me an x value. And I'm going to make a distribution of my x. Cool? Yeah? So all this code at the bottom is just to make a distribution.
So we're using the on lattice parallel that we just did.
No, this is just, we don't really have an external force here. We don't really have those problems.
Oh, so where do we have a probability of sitting still?
It just happens.
If we try to go down the potential and it
Exactly. Cool? People okay with this? Anyway, that's what I want. This is what I get. Okay, it works really well. Cool, because I'm not spending all this time sampling like space anymore. I can sample where stuff is actually going on. Function. Okay, so this gives me a nice resolution for it. Cool. Okay, so this is just talking about drawing random numbers from a sample. But I've tried to pepper it with reminding you of Boltzmann because we can now take this, and instead of saying we know the function, we can say we know the potential. And now let's just say it's a particle bouncing around, and we just want to know what's the equilibrium distribution of particles in this system. You can have them do a random walkthrough here, where the probabilities of jumping against the potential are less likely, and when they have to go really against the potential, it's really unlikely, but you always jump downhill. And if you just look at your distribution of particles in your system, you're going to get the distribution according to what Boltzmann would tell you about the potential. Okay, but you have this extra kT factor. If you turn up the temperature high enough, okay, then everything, all the probabilities are going to be 1.
So T is the jump size.
No, the jump size is A. Okay, T
yeah.
is really like the is like the volatility.
Yeah, but where does it come into? Right, because we described the algorithm without ever touching any constant potential. So where does it? From that, how do we?
There is no KT. You only evaluate the function. Right? So without the potential, the probability is just this. There's no T in it.
Yeah, but what?
Right? So if we're just drawing random numbers from a distribution, this is all we need. We don't need a KT at all. But I'm trying to make the connection to, you know, this is totally, if we just look at like a potential landscape, we can do the same thing for the particle, but we have another factor in here. What's the temperature? Right? If the temperature's really low, everyone's going to be sitting in the global minimum. Temperature 0. When it's really high, everyone's going to be flying across to the temperature. Okay, that doesn't come into here at all. Okay, but it's an extra thing that comes in when we try and make the application. Cool? Which is where we want to start kind of going. All right. But again, so this is an easy way to introduce the importance sample. Okay, but this whole idea of having our jumps weighted by the Boltzmann factor is going to come into other applications. Okay, and that is, so this is importance sampling, this is metropolis, but the metropolis is really that you weight the probabilities by the Boltzmann factor. Cool? And we'll see what we can do is we can construct a system, calculate the energy of the system, and we propose some change to the system. And we accept that change based on the energy of the system between 2 points. Cool, but we'll look at that explicitly. Yeah? Okay, but we're getting more abstract. Okay, so now you can start applying this whole things are jumping around to the anything. Cool? Yeah? Cool. All right, so let's get there. It'll be fun, because then we can get to viruses or bacteria swimming in solution. Right? Super crazy complicated, it's just a particle jump. So